Well, welcome everybody to this webinar on automatic application program creation based on conceptual design information. This is the second session of today on this topic, and we had some good questions early in the morning. So where possible, I'll make sure we'll talk about those as well today. I assume most of you are familiar with the exida webinar concept. The audio is provided via the GoToWebinar application over the internet, so make sure your speakers are enabled, and your microphones are automatically muted, so you won't be able to talk. However, there is a question panel on the right-hand side, and you can ask any questions through that panel. I will be able to see the questions, I will read the questions and answer the questions to my ability. So use that feature on the right-hand side of the webinar screen. My name is Iwan van Beurden, and I am the Chief Technology Officer, Director of Product Development here at exida. And I have a variety of roles, but my key role at exida is that I'm responsible for the development, maintenance, and certification of the Excelencia software, as well as the SILstat live event recording module within the Excelencia software tool. And that's the area of expertise that we'll be talking about today, stuff that is related to the Excelencia software. In addition, I'm a member of the ISA 84 committee, and there's a variety of functional safety tasks that I perform on a relatively daily basis, ranging from IEC 61508 development support for manufacturers through functional safety assessments and audits for end users on sites, attending site acceptance testing, factory acceptance testing, and so on. I am an instructor for exida as well as for ISA, and I am a co-author of one of the new upcoming ISA books on probabilistic modeling of safety instrumented functions. I assume most of you are familiar with exida. Exida is a leader in functional safety tools, consulting and assessments, with a deep knowledge and understanding of your project to make you achieve the safety while optimizing your process. We are an ANSI accredited certifying body for functional safety and cybersecurity. As I mentioned, myself, I'm a member of the ISA 84 committee, but we are very active on many of the functional safety committees, and we have various locations around the world where we can support your team with our local team. Let me see, there's a question here with regard to audio. Yes, okay, so that is solved. So all right, so just from a quick overview, our locations around the world. I am located in our Philadelphia office, a little bit north of Philadelphia. That's right here on the map. But as you can see, we have a number of offices around the world, and basically can cover every time zone available. Our main products and services include consulting for process safety, or IEC 61511, control systems, cybersecurity, and alarm rationalization or alarm management, as well as overall process safety management. We do product certification. Most of you have seen products that were certified by exida for the IEC 61508 standard for functional safety, but we also do functional security, security lifecycle, and overall cybersecurity certification on products, basically anything that has an Ethernet port. We do training classes on process safety, control system security, and alarm rationalization, and those can be either online, on demand, or on site. Then we have a variety of engineering tools, with Excelencia being our main product, and we will talk about that today. And we have a variety of reference materials, data books, tutorials, and so on. The Safety Equipment Reliability Handbook is one of our key reference books that we use. And then finally, we do professional certification with the Certified Functional Safety Expert program, where we have the CVSE, the CVSP, as well as the Control System Security Expert certification. So today we're going to get started with a short introduction. The main objective of that introduction is to make sure that everybody's on the same page. Then I'm going to look at IEC 61511 at a high level and see what specific requirements there are in the standard with regard to the application program. And then we're going to look at conceptual design and how a conceptual design SIL verification dictates requirements for the application program. Once we've addressed that, we'll look at the overall benefits of automatic logic creation, and then after that we'll have a demo of what is a pretty far advanced proof of concept of automatic logic creation, and then we'll talk about some beta projects at the end as well. So from an introduction perspective, I think it's important that we all understand when I use the word application program, what I mean with that. It's the configuration that is implemented in the safety PLC to apply the conceptual design in hardware. And in some cases, that is referred to as application logic or configuration logic or just simply logic. In some cases, it's referred to as a configuration program or logic program or application code. IEC 61511 talks about application programming, so I'm using the words application program throughout this webinar. Usually, the application program is developed using some form of a limited variability language, which are the IEC 613, IEC 613 languages, structure text, ladder logic for sequential function chart, and function blocks that we typically develop our application logic in. So when it comes to the application program, IEC 61511 has specific requirements for that generation of that logic, and let's see as to what the standard has to say about that. First of all, I'd like to point out, and that's the item you see here on the right-hand side, that when we talk about the design phase for the safety instrumented function, safety instrumented system, which is covered in clause 11, there's a separate clause that talks about application programming, clause 12. So there's some emphasis there in the standard with regard to application programming. On the left-hand side, what you see is a screenshot from the red line version. So that's IEC 61511 2016 RLV for red line version, which basically shows the differences between the 2003 edition of the standard and the 2016 edition of the standard. And one of the things that we see is that the word software, which was a little bit vague in the 2003 version of the standard, has been replaced by application programming. So there's an increased enhanced focus on application programming in the 2016 edition of the standard. So what does the standard mean? Application programming, well, they even talk about an application program lifecycle. And there's a definition in the standard: activities occurring during a period of time that starts when the application program is conceived and ends when the application program is permanently disused. And associated with that is a life cycle that you can see here, application programming safety life cycle, specifically focusing on the creation of the application program. And in addition, when we look at configuration management requirements, a new clause in the standard, clause 5272, now talks about the safety instrumented system software, hardware, and procedures used to develop and execute the application program shall be subject to configuration management and shall be maintained under revision control. As a note, the system software includes application program, logic solvers, embedded software, and so on, and utility software tools. So the reason I'm showing these two particular clauses because they're new in the standard. They're clarifying what is meant with the application program lifecycle, as well as some of the requirements with regard to the application program lifecycle. And on the next slide, I show the inputs and outputs of the application programming safety lifecycle. So that's what you see here on the left-hand side. And it's not my intent that we actually read all of this, but whenever you see something in green in the redline version of the standard, it is new. So this entire life cycle, including the inputs and outputs, has been redone in the new version of IEC 61511. Also, if you look on the right side, these screenshots of these 5 pages, and again, it's not the intent that we read all of this, but this is the entire clause 12 on the standard. It's completely green. It's completely redone. So when I say there's an enhanced focus on application programming in the standard, you can see how that is visible when you just look at the redline version of the standard. So it's completely redone, rewritten, and updated to what is realistic for end users. And some of the things that you will see in there is it talks about consistency. It talks about the use of, let's say, specific coding standards and approaches to come up with an application program that is functionally safe. So that is just as a nutshell as to what the standard does with regard to application programming. All right, so how does that apply to us? Well, when we follow the functional safety life cycle, we do our process hazard analysis, we do our layer of protection analysis, we come to the conclusion if we need safety instrumented functions and a safety instrumented system, we know what the SIL levels are for each safety instrumented function, and after that we start to develop a conceptual design, a safety instrumented function that will be able to protect against a particular hazard. And when we define that conceptual design, there's a lot of information that we are documenting on what the eventual application program needs to look like. And of course, everybody's using Excelencia Silver tool. The Silver tool is the key tool for evaluating the achieved SIL level, doing a SIL verification based on the conceptual design that you come up with. So let's look at the conceptual design and see what type of information is available, is defined basically, that we need to include in our application programming. Well, let me get my spotlight here. The screenshot you see on the left is from Silver, and it is the configuration of a particular sensor group. And there's quite some information in here. So let's start here with the voting. In this particular case, I have a 2 out of 3 voting. And that 2 out of 3 voting tells me, number one, the number of inputs and outputs, or in this case, inputs. It's a sensor group. So it tells me there's 3 inputs. It also tells me that the voting is such that if 2 of the 3 indicate I need to go to the safe state, then I need to go to the safe state. Next, in our configuration options, we specify if it's a high trip or a low trip. In this case, it's a high trip, meaning that if the process value goes above a certain set point, we transition to the safe state. So when we program application logic, that's one of the items that we need to know. We need to know when does the system transition to the safe state, when the value goes above a trip point or below a certain trip point. So that's something we specify here. Next, we talk about outer range detection. We need to be able to detect, for example, transmitter faults where the output is driven to a predefined fault range. So, for example, 3.6 milliamps per the NAMUR 43 guideline. If we say that we detect those types of failures, then we need to program for that. So out of range detection now is specified here. Do we filter out alarms? So if an alarm occurs, do we have the ability to wait a little bit before we transition to the safe state, or do we immediately transition to the safe state? In this particular case, I said no, it's off, so we're not filtering, but that is an indication if we need to do a trip delay. Well, there's a question here. So I'll come to external comparison in just a bit, Louis. When we have an alarm voted as trip, if you want to transition to the safe state when there's a fault detected, then that's an action upon transmitter fault. That needs to be programmed in your logic solver. And you'll notice there's no box here on the external comparison. The reason for that is absolutely external comparison is something you would need to program as well. But in the proof of concept that I'm going to show you today, we don't have the functionality yet that you can specify what the tag is that you're going to do the external comparison with. So that is something that we still need to implement, and what I'm showing today is functionality that we have today in our let's say advanced proof of concept. But yes, to your point, if we can specify the tag that the external comparison is done with, then absolutely we can program that as well. Some other information that we specify in the sensor group are the tags. So there's this tags option. If you click on that, you see all this. Now here's your tag names. In this example, I'm talking about PT1492-01A, B, and C, with ranges of 0 to 135 psi and a limit value of 120. All that information is information that you need to program in your application program. So within the sensor group, there's a lot of information specified that you eventually will need to transfer into application logic. So next let's look at the logic solver. All right, that's not so exciting. The logic solver, of course, from a conceptual design, you just select the type of logic solver you have. This is where all the logic is going to be implemented, but there's not a whole lot of programming levels, programming information specified here. What is specified, though, is if you have multiple controllers, to what controller the particular safety instrument function belongs to. So in this case, you'll see it's a tank farm name on the controller. That's the controller that this particular function belongs in. Then lastly, we have conceptual design for the fine elements. So again, we see a screenshot here from the silver tool. The screenshot shows the configuration of a fine element group. And one of the things we configure here is the voting, and the voting tells us, in this case, one of the two, the number of output channels. You'll see that unlike the sensor group, where I said it tells us the number of input channels, I had a second bullet that says it tells us the voting. You won't see that here in the fine elements, because how does the logic solver typically work? The logic solver doesn't pick and choose which output to energize or de-energize. It just de-energizes both in case of a trip, assuming a de-energized trip system. The piping of, let's say, two valves that need to close dictate what the voting is. So from our modeling, we need to know, are the two valves in series closing on trip? One of the two. Are they in parallel closing on trip? Two of the two. But for the logic solver, there's no difference. In both cases, it will drive the fine elements to go to the safe state. In addition to that, we can specify tags, so XV1492-01 and 02, and the action, in this case, closing on trip, is specified. And in this case, you also see it's a de-energized to trip action, not an energized to trip action. So those are things that we specify in the final elements that we need to know when we configure our logic solver. So the next aspect of conceptual design documentation is when we dive into our design SRS. In the design SRS, we specify information like how do we handle maintenance overrides, how do we deal with bypasses, how do we deal with startup overrides. So if you have a low-level trip, you need to make sure that there first is some certain level in the tank. You need to bypass either for a certain period of time based on a certain event or based on a certain variable giving a certain value. So that can be configured. Then, if we do have a trip delay, so if we filter out transmitter alarms or faulty signals, we need to specify that time intervals, and we can do that here as well. So you see these, 3 or 4 boxes here immediately tell you what are the maintenance overrides, the bypass management, the startup overrides, and as well as your trip delays that you need to configure as part of your logic. And lastly, when it comes to inputs, we have auxiliary inputs. Now, we all know that when we model a safety instrument function, we only model those pieces of equipment that are absolutely needed to detect the hazard and bring the process to a safe state. anything extra is typically not considered part of the safety instrumented function. So we could have additional inputs that we may want to trigger the same events, but if they're not part of the safety instrumented function, we wouldn't include them in our SIL verification. But in the design SRS, where you're specifying how does my safety instrumented system need to be implemented, we do, of course, need to specify what those auxiliary inputs are. On the final elements, if I drop to the bottom here, we need to specify what our auxiliary outputs are. Again, we model in our SIL verification, in our conceptual design specification, only those actions that are absolutely needed to achieve the safe state. However, if there is if there's any additional actions that we want to take, we can specify them here. And what you can also specify on the final element portion of the design SRS are the reset options. So how do you perform a reset? Is that done manually through an HMI, or is there logic associated with it? Remember the energized to trip versus de-energized to trip concept. So all that is specified in the design SRS, which are the detailed requirements that are being put on the safety instrumented system. This information, the conceptual design and the design SRS information together, tell us how we need to program our safety PLC. So if you have this information in electronic format, you can print it, and then you can read those printouts and start programming, or you just have that information available in your electronic format already, and you just transfer the information. And that makes your life cycle a lot easier to manage. And there's a lot of typing that you don't have to do. So that brings us to the benefits of the automatic logic creation. And now, you create the logic automatically. Therefore, you guarantee consistency with the design that was originally specified, and any implementation errors are avoided while you're trying to interpret and just transcribe the design information. As I mentioned, as some of my tasks, every now and then I attend the factory acceptance test, and we see quite often that the input to the original logic creation is a cause and effect matrix. And then we see that that cause and effect matrix gets interpreted and then programmed in the logic solver. Well, I was at one factory acceptance test, and we looked at the cause and effect matrix, and everybody interpreted the cause and effect matrix in a consistent manner. So you would think the application code is right. Well, then there was one of the engineers who was actually explaining how the process worked, and we all realized that there were two interpretations to the cause and effect matrix, and everybody had the wrong interpretation. So the conceptual design, which was clearly documented in silver, which was unambiguous in silver, became ambiguous in the cause and effect matrix and resulted in an incorrect application program. So we had to fix that. Okay, that's why you do factory acceptance test. But this, your simple copy and paste error. Instead of a trip limit of 135, I accidentally typed 105, and you may have more spurious trips than you intended. Also, because the programming only takes a fraction of the time, because you click on a button and your logic is created, your conceptual design can be completely finalized before programming starts. Usually, due to project schedules being very tight, implementation starts before the requirements are completely finalized. So we start to implement our logic solver, we start to program our logic solver, and we don't really know what the requirements are. And some changes could be very simple. Oh, I assume the single transmitter, I come to the conclusion I need a 2 out of 3 voting. Oh, I assume the single valve, I come to the conclusion I need partial stroke testing. So those simple changes obviously result in rework. By being able to shorten the programming portion of the whole project, your project schedule will be much smaller, but there's also much less rework. So there's a dramatic impact on your project schedule, and because you can enforce coding guidelines, there's more consistency, and you can automatically get compliance with the requirements of IEC 61511. So those are a lot of benefits that that you can get from automatically creating your logic. And we have a webinar next week that is going to talk about how you can reduce your overall project lifecycle cost by using exSILentia, and this automatic logic creation is going to be a big part of that. So tune in for that one next week. It's going to be very interesting, and you can see some big money gains by having a nice integrated safety lifecycle tool. So, all right, we've seen the concept, we've seen the benefits. Now let's look at the actual proof of concept, or advanced proof of concept. We're getting towards the end here, where we're starting some significant testing, and starting to roll the tool out to some beta sites. We're going to look at the Delta V sys configurator that we've created. So that's everything I mentioned so far is pretty generic, applies to all logic solvers. In our case, we have created a Delta V sys configurator because we have an active project with a large oil and gas end user who is basically demanding this for that project, that the logic is created automatically. So that's what is the driving force for this particular logic solver. But the concepts, of course, are not limited to just Delta V SAS. They apply to all potential safety PLCs. But we'll see how what we've done so far, how that is translated into a Delta V sys logic, and we'll do that with a demo. So I'm going to the exSILentia software. Make sure that everybody sees the exSILentia software. Yes. So in the exSILentia software, there is I've created a project, a very simple project with a couple of different things to identify. We have some SIFs that are related to a batch reactor, a batch chemical reactor. We have some SIFs that are related to a steam turbine. We have some SIFs that are related to a tank farm, and then we have that SIF that I showed you earlier, the screenshots of where we have a 2 out of 3 voting driving 2 valves. So we're going to play with that a little bit. You're going to see what the impact is of some of the selections, and then we're going to go back to some of the other functions. I'm going to point some things out that we will then see in the logic as we create it. So I'm going to the Silver tool, and I assume most of you are familiar with the Silver tool. And in the Silver tool, we model our conceptual design. In this case, a single sensor group with a 2 out of 3 voting, going to a logic solver, driving 2 outputs. So let's look at that sensor group. We saw the high trip. We saw that the outer range detection is on. We've seen the tag information. So in here you see PT 1492-01A, B, and C, and you see ranges. And just to make sure that you all see that this is a live demo, that I'm not using a file that we pre-created, let me just change these ranges. So instead of 0 to 135, I'm going to change that from let's say 0 to 152. 0 to 152 and 0 to 152, and I'm going to change the trip point from 120 to, let's say, 136. So if you look this morning, or if you were able to attend this morning, you'll notice these are different numbers than the numbers I used this morning. So again, that's another indication this is a live demo. But I've specified my tags, my ranges here, my trip limits, my engineering units, and so on. So that is my sensor group. I can go to my final element group. The same story here. I have my tags. Let me click on that. The tags here: XV 1492-01, 1492-02, closing on trip. That matches up with what I specified here. And the logic solver that I want to assign this to is apparently called the tank farm logic solver. So that is a simple function: 2 out of 3 input, 2 outputs. Nothing too special, but we'll see what happens when we start to convert that. So let's look at some of the other functions that we have in here. We have a steam turbine in here. And what you will see when I open this function is that there's a steam shutoff valve. And that steam shutoff valve, just a single valve, 1 out of 1, is used by all all the functions that are in the steam turbine scenario. So if we look at the silver menu and we go to group reuse, you will see here that for the final elements, that steam shutoff valves is used 4 times in SIF 1, 2, 3, and 4 that are associated with my steam turbine scenario. And this is SIF ST-SIF 001 actual position. So we have a 2 out of 3 voting on the inputs. We have a logic solver, and you see that's that steam shutoff valve output. We go to the overspeed, 2 out of 3 voting in this case as well, and you see the same shutoff valve. And just to see, it's the tag is STXV002. If we go to the loss of loop oil, you'll see it's the same tag, STXV002, the same valve, as well as for the last one, which is the SIF 004, that same steam shutoff valve. So it's the same valve that is used by all 4 of my steam turbine SIFs. And we can easily model that in silver with the reuse group. Then let's look at this batch chemical reactor. What do you see here? We have a simple input, high pressure going to a single valve, the drain to the quench tank. We'll come back to that in a little bit. Then we have one that's a little bit more complex. That's a reactor overfill. We have a single input. We have 2 outputs here, reactant A feed and reactant B feed. And you'll see that both need to happen in order to prevent the overfill scenario. And now if we go to the first one, SIF 500, it's a high temperature scenario, single input, but what do we see? That stop reactant B feed is part of both SIF, part of the overfill SIF as well as the high temperature SIF. And notice this is XV504, so you will see that in a little bit coming back as well. So in this case, 2 final elements that need to, 2 final element groups. One is the cooling jacket and one is the reactant B feed that needs to stop. Lastly, let's look at these tank farm SIFs. They are not very special. They're just simple one-to-ones, 1 input, 1 output. But what you can see here is that if we go back to the SIF identification, you'll see that we specified that this is part of this tank sheet. So there's something special with these SIFs. And basically what is special is we specify that they need to be part of the tank sheet. So whatever that means. So we'll see that in a little bit. And you see that this last one, for example, is not part of the tank sheet. All right, so that is a quick overview of some of the settings. There's a little bit more. So let's go back to the overpressure event. The silver scenario, we see the drain to the quench tank. Look here in the design SRS. You'll see in the design SRS, in this case, that there's 3 auxiliary actions. XV501, 502, and 504. In addition to XV500. So there's additional auxiliary actions, and apparently we do that through a parameter, whatever that means. So that is something that we've configured here. And then up here you can see your maintenance overrides and all that. Here's a how do you alert an operator when the bypass is about to time out in 5 seconds and things like that. So all that can be specified in the tool. So once we have completed our conceptual design, we've specified everything in the SIL verification, we've done our additional specification in the design SRS, we can then create the logic. So what we're going to do here, we're going to this the SRS C&E menu, and we'll see 2 menu options related to Delta V SIS. The first one is Manage Delta V SIS configuration, so let me select that one first. For those of you who are familiar with Delta V SIS programming, there is a possibility to have composite blocks within a project. A composite block can, let's say, replace all 2 out of 3 blocks within a particular project. You specify the composite block once, and then throughout the logic creation, this configurator will automatically replace the standard 2 out of 3 voting block with the composite block. In this case, I'm going to keep it simple. We're going to just have the standard blocks but this composite block definition is already functioning in our current proof of concept or advanced proof of concept. We can also specify the number of CIFs that are maximally allowed on a sys module. In this case, we leave it at 0, which is unlimited. And then the target platform. So in this case, we're working with Delta V version 13. So that's our target platform. So that's the management aspect of the configuration. And then when we go in the next one, we actually go and generate the logic. So let me generate Delta V sys configuration. You will see the dialog appear that we also saw on the slide. There's some description here. I'm going to export everything, all CIFs, and I'm going to export everything in one file. When you first create your logic, when you first create your initial program, it makes sense to just do everything at once. If you would have a little tweak to a particular safety function, you may get to a point where you say, hey, I only want to export this one safety function, or I want to export the safety function in separate files and only import the one file that really changed. In this case, I'm just going to export everything at once. And we're going to export CIF to an FHX file by a simple click of a button. And the file that we're generating is called sample project. Look at the timestamp here at the end, 2017 0309 1638. So it's 4:38 p.m. East Coast time. That's the date on the file that I just created. And I'm already done. The file already exists. So hit OK here. We see a quick summary of the configuration that was done, as well as an error list. So if there will be any errors during the conversion, they would show up here. In this case, everything is just fine, no errors. So let me go to my folder here, and you'll see a couple of a test file before the first webinar, the test file of the second webinar, and then here's the test file of the of this webinar, and we have the simple log file, everything that happened. And then here we have the FHX file. So I'm going to copy that file, and I'm going to go to my virtual Delta V environment. And in my virtual Delta V environment, I'm going to say I want to import a standard Delta V format file. And in my case, that is, I'm just going to paste that file here. Actually, let me create a new folder so you can, so it's easier to see for you where I am in the file structure. So I'm pasting that file that I just copied here. You'll see it's the exact same name. 1638 was the timestamp, so that's the one that I just created. I select it. I hit open. There's a couple of messages here that I just know I have to hit no to all, but that's just because I'm importing. And as I import, you may have seen that here on the left-hand side, certain areas were added to my configuration. There's an area for the batch reactor, there's an area for the steam turbine, an area for my tank farm, and an area for vessel V1492. Hey, that was the CIF that we play with. So let's open that one up in Control Studio. So open in Control Studio and maximize this screen real quick and zoom out a little bit. And what do we see? Let's see if the spotlight works here. We see 3 inputs going into a voter, driving a CEM block, driving 2 outputs. So now that we've seen that, I have to get rid of my spotlight again. Let's zoom in a little bit. And what do we see? We see that the input here is called PT_1492-01A, B, and C. Those were the names that I gave to my inputs, the tag names of my inputs. We'll see that at the final elements, XV1492-01 and -02. Those were the tag names for the final elements in my function. Let's look at the voter. When I click on the voter, there's this parameter information available here on the left. And one thing that we see is there's 3 inputs. The tag names are put into the description of the 3 inputs. We see greater than. we had a high trip. So if the value that I'm measuring is greater than the trip point, we need to go to the safe state. The range is specified as 0 to 152. Remember, I changed the 135 to 152, and it's PSI. So that didn't change. And we see that here, that's the scale. If I go all the way to the bottom, you will see the trip limit here at 136. We changed that value from 120 to 136 in our file. You will also see here that the number needed to trip are 2. I got 3 inputs. 2 out of 3 need to go to the safe, indicate that I need to transition to the safe state for my safety function to act. So all that is taken care of in this analog voter. That analog voter is generating an output, and that is a single output that then drives to actual output. So a single output of the analog voter becomes a single input into the CEM block, which is driving 2 outputs, XV 1492-01 and 1492-02. So that is our, our relatively simple safety function, 2 out of 3 voting, driving to fine elements. So let's look at, let's say, my steam turbine. So I had 4 functions on the steam turbine, but I only have 1 logic sheet or 1 sys module. Let me open that up in Control Studio and expand that. And what do we see? 1 output driven by 4 causes, or driven by 4 inputs. Each of these is a separate safety function, but the tool knows it's the same fine element that's being driven. So we have, let me zoom in again, we have overspeed, voted 2 out of 3. We have actual position, voted 2 out of 3. We have loss of loop oil, voted 1 out of 2. And we have vibration, voted 2 out of 3. Those voters are in here. These are digital, so there's on-off signals. The number to trip is here. We have 3 inputs. There's my 2 out of 3. For the analog here, we have number to trip 1. 2 inputs, 1 out of 2, and so on. Resulting in 4 causes in my cause and effect block, 4 different safety functions, all driving a single output. So that is pretty cool. The tool knows that that same fine element is part of multiple functions, and it nicely puts all that on the same logic sheet. Let's look at the tank sheet. The tank sheet was interesting in that, we had these 5 functions. They were very simple, all 1 out of 1 input, 1 out of 1 output. But we marked them that we wanted them grouped on 1 sheet. What does the tool? It groups them on 1 sheet. You'll see 5 inputs, 5 outputs, 5 causes, 5 effects in the CEM block. If we open it up, you see that each input only drives 1 output. So very straightforward. Each SIF drives its own output, has 1 input, drives its own output. The only thing the tool did, it nicely placed them on 1 logic sheet, so it's easy to look at, easy to maintain. And then lastly, let's look at our batch chemical reactor. And we're going to start off with this 501 function. That was the overpressure of the chemical reactor. It had just a single input, 1 out of 1. It was an analog, so there's an analog voter. In this case, the voter is just a 1 out of 1 voter, but that's where all the logic is happening. So the greater than, the ranges, the trip points, all that is specified there. And you see there's a total of 4 effects. Only one of them, the XV500, is part of my safety instrumented function. The other 3 are auxiliary outputs. Remember that I showed you that you can specify auxiliary inputs and outputs? Here's 3 auxiliary outputs that are specified, and in this case they're specified as parameters, and those parameters can then be linked to the actual outputs. So that's pretty neat. And then lastly, let's go to the last batch chemical reactor sheet. That one was a little bit interesting in that we basically had 2 functions. I'm going to zoom out again. We had 2 functions. One function was driving, was closing A feed and B feed. The other function was doing a couple other things, but it was also closing the B feed. The B feed, total of 4 actions. The B feed was XV 504. So you see that right here. So that should be part of both functions, both inputs in this case. So let's look at what the cause and effect block does. We have SIF 502 drives 2 outputs, de-energizes 2 outputs, feed A and feed B, and SIF 500, which de-energizes the reactant feed B. So you see that this particular output is driven by both of the functions. And again, because we're reusing a final element, the configurator knows that those that is the same final element, that they need to be nicely combined on one logic sheet or one assist module within the Delta V environment. So that is in a nutshell what the configurator does. Let me close this and go back to the tool. If you are familiar with the exSILentia software, you may know that we have the ability to create a cause and effect matrix as well. I'm just going to do that for this particular project, so complete project cause and effect matrix. And the reason I want to do that is so you can see that what we just configured in the logic solver, we can also see in a cause and effect matrix. So, for example, my 4 steam functions all drive the same final element, and you can see that directly in your cause and effect matrix. The batch chemical portion, we had the one function that excuse me, that drove reactant A and reactant B, and one function did a couple of things in reactant B, and you see that that overlap here again. And then for my tank farm, you see the same behavior that we saw in the CEM matrix. You see that here in the CEM block. You see that in the cause and effect matrix, as well as the 3 inputs. 2 out of 3 voted. Here's your vote. Here's the description of the vote. 2 out of 3 voted that were driving the two outputs. So that also, again, confirms what we already modeled in the configurator, through the configurator, and therefore the logic that we generated for the Delta V system. And that is a confirmation. You could use that during your SAT testing when it comes to verifying that your installed system is indeed doing what it's supposed to. So we go back to my slides now. Now we saw the demo. We saw how it works. From an exSILentia perspective, we have a variety of tools. We have tools that relate to functional safety. So we do our PHA and process hazard analysis, your LOPA and the layer of protection analysis, SIL selection, safety requirements specification, and SIL verification. In the management column, we already have an alarm rationalization, alarm management tool, as well as our lifecycle cost estimator. And we can now add that logic solver configuration to that management category. We of course have our cyber risk assessment tool, CyberFacts, and our maintenance tools, the proof test generator, as well as our live event recorder, SILstat. So all this fits nicely within the scope of what we're doing with the exSILentia software. Brings us to the subject of beta projects. And it shouldn't be a surprise, since this is a project driven by a large oil and gas company that has already picked Emerson Delta V as the logic solver for this project. That's where the logic creation project started. And that's the reason why we're doing logic Delta V SIS logic solver. So we're working closely together with Emerson on this. We're talking to a variety of end users who may want to be interested in, who may be interested in participating in a beta project. If you already use exSILentia and you document your conceptual design using exSILentia, then obviously automatically generating your logic for Delta
VSIS is almost a no-brainer, assuming that you're using Delta VSIS. So if you want to participate, you can contact me at my email or through LinkedIn. Keep in mind it's a beta project that has some benefits financially for you. There are some expectations, of course, that we would have for you, and if you contact me, we can talk about what we would expect from you and what you can expect from us as well. So if you're interested in that, just reach out to me, or through your local Emerson contact that eventually will come on my plate through our contacts with Emerson, and we can see if your particular project is suitable for demo. So with that, if there are any questions, feel free to type those in the question and answer field. I see a couple here. One is this limited to just Delta VSIS? Well, currently yes, because that's an active project that we have. The concept is not limited to Delta VSIS. We would implement this in other logic solvers as well, provided there's a project for it. So that's the current situation for that. Here's another interesting one. That's sometimes a little bit up for debate. If you have generated the logic automatically with your Delta VSIS configurator, could that mean that we don't have to do the FAT? Well, I think it could. I'm not going to say an absolute yes, you can. I'll have to talk with our legal representation here, but in reality, the intent of an FAT is to verify that the application logic was created correctly. The intent of the FAT is to verify that what is programmed in the logic solver is indeed corresponding to your requirements in your safety requirements specification and your conceptual design. So if you automate that, that could be a good argument why you don't want to do the FAT anymore. Obviously, before the hazard is present, you're always expected to do a site acceptance test, but you could skip the FAT step quite most likely. Here's another question that goes into the licensing. The logic generator is a plugin to Excelencia. It relies on the Excelencia software. It relies on the information that is in the silver file. It relies on information that is in the design SRS. So it's heavily relying on Excelencia, so currently it will be available as a plugin to the Excelencia package. So if you're familiar, if you're already using Excelencia, it's a small add-on. If you are not using Excelencia, then yeah, you would have to acquire Excelencia as well. In reality, if you do your SIL verifications, if you do your design specifications, then that should be a relatively straightforward approach. Can we modify the module template after it's built? So yes. So so once the Excelencia Delta V configurator generates the logic, you import it into your Delta V sys system. It will say that the logic was generated by Excelencia. As soon as you make a change and basically save the sys module again, it will say last saved by whoever is the person that's logged in. In my case, it's administrator. In my Delta V environment, I'm an administrator, and because we have multiple people using it, everybody's administrator. It would always say that it was changed by administrator. But if you have it set up correctly, where your actual username is used, then it would say, yes, this person has changed it. So yes, you can change the module. We would recommend that if you need to make a change, that you make that in Excelencia and re-export. That way, your conceptual design is up to date, but it wouldn't be limited to that. Here is a question, and that's a little bit outside of the scope, but it talks about if we have information in an Access database on the different safety instrumented functions, would we have to re-enter that into Excelencia? Well, the short answer is yes. I mean, the information needs to get into Excelencia. The little bit longer answer is you may want to reach out to our application support desk. We have an application support group that will be able to help you with importing information. So they do a lot of importing because we have some standard importers, but pretty much every customer customizes their PHA, for example. So when people are changing from their traditional PHA tool to the fax module within Excelencia, one thing they don't want is lose past information. So they ask us to import, and we can very easily, through our application desk, help you with importing that information. So yes, the information needs to be entered in Excelencia. So if you have that in an Access database, we can probably help you with an import if there's a good match between the fields. Here's another one. This is a little bit outside the Delta V configurator, but it's a nice question, so let's look at it. So if we do external comparison and we're using a BPCS signal to do the external comparison, does that signal have to come into the logic solver via a signal splitter, or can it also come through communications, for example, Modbus? Either is fine. The one thing to keep in mind is that if you use serial communication, there's usually a little bit of a delay. So if this process is very dynamic, it may not be a good up-to-date value to basically compare with. If it is a slower value, then yes, serial should not be a problem. If you split it, obviously that delay is not an issue. But either one could work. All right. Yep. And here's another comment. Validation checklist. Generated out of Excelencia. Yeah, that is on the to-do list. That is definitely something that we're looking into to enhance the overall lifecycle experience with the software. All right, if you are interested in knowing more, if you want to know more, we are presenting and exhibiting at the 13th Global Congress on Process Safety. That's by the American Institute of Chemical Engineers, the Center for Chemical Process Safety, which is happening at the end of this month, March 26th through 29th in San Antonio, Texas. I myself will be there, as will be Kate Hildenbrand, who is one of our product sales engineers, as is Todd Stauffer, as is Denise Chastain-Knight. We will be at booth 530, and as I said, we will be presenting and exhibiting. And if you want a live demo of this or any of the other lifecycle tools within Excelencia, feel free to stop by. We'll be happy to give you a demo at the Global Congress on Process Safety. And I've heard that San Antonio is an awesome place to go to. So if you need an excuse, here it is. Visit us at booth 530. If there are no other questions, thank you very much for attending. Recording of this webinar is going to be made available probably tomorrow or early next week. You will also get a copy of the slides as is usually the case. So thank you for attending. If you have any other questions, my email address was in the presentation, so you can reach out to me directly or just simply through info@exida.com. If you're interested in being a beta site, contact us as well. We're very interested in working with you. Thank you very much, and until the next webinar. Take care.